Hey everybody, welcome back. I've started the live stream 30 seconds early, so I'll just wait for people to join in. Awesome. I think we're good to go. I'm just double checking to make sure we're live everywhere. YouTube looks good. Events look good. Amazing. Hey everybody, thanks for joining us again. Welcome back to the session. I actually want to start the session with a more serious message that I want to get out to everyone. My father has been admitted to a hospital because COVID made his blood sugar skyrocket. And I know this variant is supposed to be mild, but we all work in machine learning. We're in the top of, I think, the world's smartest people. Please try to stay indoors. Jeremy Howard made a video about this. He says it's essential to use N95s. I would really urge everyone to please try to minimize being in crowded areas and please consider wearing masks that are high quality. Just wanted to get this message out there without making it too serious. I'll just be back in 1 second. Amazing. I'll get started now. Thanks for joining us. So we're aiming. I've set an ambitious goal today, like always, of going through chapters 3 to 6. We're to the people who are new here. Here's my version of the book. We're reading Deep Learning with Python 2.0 by Francois Chole. He created Keras, and he was also kind enough to join us for a first session. So if you're watching this recording on YouTube or if you're joining us freshly today, I would encourage you to check out the Ask Me Anything interview with Francois. We spoke about a lot of things, and we also went through the first two chapters that are a bit of introductory, quite good starting notes for anyone who's new to the world of machine learning. And as a reminder, if you're watching this recording or if you're joining us for the first time today, all of our study groups are open to everyone. These are recorded, these are made available to everyone free of cost. And I really want to emphasize on the point that everyone and anyone is welcome to join. Please ask as many questions as you like. I love to answer any questions. If you're new to machine learning, I'm happy to guide you to the best of my ability, although I don't think I'd be the right person. And yes, please don't hesitate with asking any questions. These events, these live streams are for you, and we want you to enjoy them to the fullest. So here's the agenda I have planned for today. For the first 5 to 10 minutes, I'll try to recap what we learned in the last week. I'll announce the winners of 27 days of Keras, and then I have this ambitious goal of going through about actually 3.5 chapters. So we'll continue doing that. Throughout the session, my throat dries up really quickly, so I'll be taking breaks to answer questions, to check the YouTube chat, and to check the Bizzabo chat. That's the event where you might have signed up. Um, I'm just going over there to make sure things are looking good. Yep, I can see the comments coming, so that's good to see. Amazing. So throughout the session, I'll be taking breaks to answer your questions. Please keep them coming, and I'll keep an eye out for all of them. You don't want to see my face, so let me hide that from the YouTube video. Awesome, we're good to go now. So let me start by reminding everyone what 27 days of Keras is. It's an initiative to invite all of you to learn Keras, to spend more time learning Keras. And the only requirement is please learn something about Keras and share it with the world. I really think there's a lot to be learned by writing blog posts, by sharing your notebooks. And I want to give a huge shout out to Yuvraj. Yuvraj has been extremely consistent about his learnings, and I think I'll try to invite him in the next session to ask him really what keeps him so consistent. But every single week, he's been writing incredible blog posts. For the first submission that he made to 27 days, he summarized our previous session. So I'll correct myself. If you didn't join the previous session, please don't watch my recording. Check out his notebook instead. It's a better version of what I taught. Let me put that in the YouTube chat real quickly. There you go. Should be there. So thank you, Yuvraj, for that. Borut said he will submit a soccer prediction time series component, so I'm looking forward to that. Aritra, he's an incredible writer. He writes great blog posts at PyImage Search, which is one of the best resources, in my opinion, to learn computer vision. He had submitted VIT on small data sets as an example to Keras IO, and he was kind enough to also put this in as a submission to 27 days of Keras. So he's implemented VIT onto, I believe, Keras. Originally, it wasn't PyTorch. All of the examples in Keras, I want to remind everyone, are really high quality, and I would really encourage everyone to check them out. They're, I think, one of the best ways to go about learning Keras if anyone is at all interested. So anything on, sorry, keras.io, I would really encourage you to spend more and more time on there as we go about learning Keras. And I also want to mention Aritra won the week's 27 days of Keras. So Aritra, if you're watching or if you're not, we'll reach out to you to offer you some swag. As a reminder to everyone, please keep these submissions coming in. As you can see, you can just take the session, which is not the best one, I'll be honest, and rewrite it. And those are also great submissions. So there's no bar to what you should submit. Anything that you learn, I would encourage you to write about it, because it serves as a good placeholder on your resume, and also as a good sign to the community that you know something. Let me close these tabs real quickly. And for a recap, we learned about what is AI, broadly speaking, what is machine learning. We learned those different jargons. Where does machine learning come into the terminology of artificial intelligence? What is deep learning? Is it a subset of machine learning? Are those two different? We looked at the code from the first two chapters and trained our first neural network. It was a naive implementation, a naive dense implementation, if you all remember. And we learned about tensors. What are they? How can we apply tensor operations? And we learned the mathematical founding blocks of neural networks. So that's what we learned from the first session. As a reminder, I suggest homework. It's just as a suggestion, but I had suggested that you should have checked out different data sets in Keras. Would encourage everyone to again play around with keras.io. We studied gradient tape, and Yuvraj did write about it as well. So I'm happy to see that at least someone did the homework. And as machine learning engineers, you're expected to spend more and more time inside of code. So my suggestion was, please try messing with the default examples of the notebook. If I hover over to any chapter right now, I see TensorFlow ones here, I see TensorFlow zeros. Just start by the simplest thing, changing these numbers, looking at the signature of this function. What's the signature of a function? It tells you what the function takes in and gives out. So if you put a question mark against anything, it gives you the details of the function. So this one creates a tensor with all elements. I admit this is like a bad example to choose from, but the message I want to get out is, please spend more time inside of here. Last week we learned about activations. My old intuition would be to go to Google University and look up what are activation functions. Would you say this is the right way to learn? Not at all. I would encourage you to instead search this, but inside of the Keras documents. So let's hover over to the docs and let's search activation function. That doesn't give anything. So let's simply look for activation. Layer activation functions. That looks like it. And instead, I want to remind everyone that as a engineer, as a researcher, as a research scientist, you're supposed to develop stuff in code. It's important to understand how these things work. But the intuition, in my opinion, comes for spending more time coding these things. So instead of trying to looking up the theory around things, build the intuition by building code, writing code, and building these models instead of understanding how they work in theory. Uh, In my opinion, that's again a strong take, but I think that should help you more than simply just reading theory. So, sharing the outline, we were right about in the starting bit of chapter 3 in the previous call. And for today, I'll try to go right up to the mid part of chapter 7. So, this session would be, I would imagine, around 5 weeks, at max 6 weeks long. And hopefully, thankfully for you all, you don't just have to study from me. I've also reached out to many experts in the world of Keras and TensorFlow experts. They'll be joining us in the next few weeks and teaching us about more things outside of the book. I'll announce more about that once they confirm, but we have at least 3 or 4 people who will be coming into teaching, coming into this session and teaching us things. Are there any questions so far about the previous session? Let me take a look. Karthik mentioned he missed the opportunity to start on 27 days of Keras. There's no start or end date. It's always ongoing. It's like 100 days of code. There's no start or end to it. It's 27, but it's also 365 days. So join anytime, please. It's for you to learn. And the reason why we're also sending out swag to people is to encourage everyone to really learn this. I'll take a quick pause and resume. Someone told me my throat really dries up really fast, so I'm trying to stay hydrated and I'll continue now. You'll see me take a lot of breaks today, that's why. Again, a refresher. How is deep learning different with quote unquote traditional machine learning? You were required to handcraft a lot of features and do a lot of manual hand tuning. So you had to define a lot of conditional statements, let's say, uh, not conditional statements, but even I'm trying to think of a good example. So if you were to just take image processing, you would have to, with OpenCV, that's one of the go-to traditional frameworks, you would have to do a lot of pre-processing, get the image into the right shape, and then be able to build a classifier on top of it. With deep learning, it just becomes a single step. So you still have to tune a lot of things, but you don't need to know as much about what's a Gaussian blur, what's an edge detection algorithm. It helps to know these things sometimes with the right pre-processing, but deep learning also does wonders without it. So next in the third chapter, I believe, Franco talks about how Keras originated, a bit of background around it. And people maybe not might not remember this, but it didn't just start out as a meta framework for TensorFlow. It was originally created as this meta library that worked with C and TK. That's a framework. Theano, that used to be a framework. TensorFlow and MXNet. So originally it existed as this hyper framework that would work with all of these options. Because earlier, remember, this was, I think, 2015, 2016. There used to be a lot of frameworks and not just the two go to ones. So at that time, Keras used to be a high level API to all of these. And in 2019, when TensorFlow 2.0 was launched, it just defaulted to the official high level API of TensorFlow 2. Um, how is this useful? It's good to know some history. It's also helpful to understand where did this come from. I remember learning about PyTorch, and there are some small biases inside of the code somewhere that originated from the original Torch version of the framework. So sometimes it's good to know these things. Today, what Keras is to TensorFlow, TensorFlow is to the hardware of your machine. So TensorFlow can talk to GPUs, it can talk to CPUs, it can talk to TPUs. You need to change some code here and there. But TensorFlow works really well on the hardware level. It interacts with the C. I think at some level it would interact at a C++ code level with the hardware, which makes things really optimized. There are some things that make TensorFlow really stand out. So it's similar to NumPy. but it tracks the gradient. And NumPy doesn't work on, you can't put a NumPy array on a GPU. You can't put a NumPy array on TPU. There's JAX, that is something different. We did speak with Franco about it, but I would encourage you to check that out. So that's why TensorFlow stands out from NumPy. These are the examples inside of the book. Small things that I wanted to highlight. So inside of these sessions, I'm again really focused on teaching you about the key things that are important, not the ones that you can simply read and understand in the book. The book would take you a few hours to read, and these sessions will be much smaller than that. So my goal here is to teach you about the important things. So I'm just trying to point those out. Now, here's the link to the repository. Let me put that in the chat. If you simply look up deep learning with Python, it should show up on Google, but let me make it visible to everyone for a few minutes. So we're looking at notebooks 3 to 7, quite an ambitious goal for today. And I'll try to explain all of the key concepts as we go along. And towards the later half, I want to make these interactive. So I have this exercise, special exercise, where we'll try to take a business problem. And as a fresh ML engineer who's just learned Keras, who's ready to make some money, we'll try to convert that into a business problem. Sorry, we'll take the business problem and convert it into a ML problem where we'll frame different questions, try to understand how we can solve it. So that's towards the, I would say, last 20 minutes. So let's start by looking at notebook 3. And this is an introduction to Keras and TensorFlow. I just gave you the history of both the frameworks and a very short description of why these are useful. Right after that, we start by looking at what things can you do inside of TensorFlow and how is it helpful. So you can create tensors and variables inside of TensorFlow. What are tensors and variables? You might ask. Let's see. Let's hover over to TensorFlow docs. Python and search for variables. A TensorFlow variable is the recommended way to represent shared and persistent state your program manipulates. So that basically means it's a variable in code. How we define variables in code, that's a TensorFlow variable that lives on your accelerator. And let's take a look at tensors. I don't think I need to remind everyone what tensors are, so I'll skip that. So what are we doing here? We're creating a tensor that has all numbers 1 of shape 2 comma 1, which means it'll have two columns, sorry, two rows and one column. And by default, it'll have a data type of float 32. So you can do that. You can also create a tensor having all number zeros. You can pick these from a normal distribution. And if you're, again, I want to remind everyone, if you're ever curious what a function is doing, put one question mark and it should bring up the signature of the function. If you are feeling very brave that day and very adventurous, put two question marks and it'll show you the source code. I'm already terrified of this, so I'll close this and read this out loud. So this example, it showcases an example that generates a new set of random values every time. Okay, so it looks like it's useful to generate random numbers. Why do we need these functions? I mean, someone put them because they are useful, right? Assumably, presumably to developers. We looked at MNIST in the last week's lecture recap of the book chapter. We looked at MNIST and we learned about different shape of tensors. Now, what we didn't learn about, how do you add those values? So inside of a variable of 28 by 28 size, having presumably the weights, how do you set those numbers for the first time? Eventually, your model learns there's a loss value that changes them, upgrades them as it loops over. But you need a way to initialize them. Or what is the first value that you start out with? So they could be zero. You could pick them from a normal distribution, define the shape, define their mean and standard deviation. Or you could also pick them from a uniform distribution. So that's why these functions are quite useful. There are different ways of initializing that are quite standard now. So I would encourage you to check out timing her initialization. We put that in the chat. This is one of the ways. And again, don't look at the theory. If you go to the paper, it's at least terrifying to me. Add this one keyword. So this looks like the right link, right? tf.keras.initializers her normal. So this is how you do it in Keras. And then you can check out the paper if you want. Turns out it belongs to the initializers class. And if I zoom over here, there are all of these ways of initializing your variables. So again, a suggested homework, maybe try initializing with these different options and see if your model trains faster. It's machine learning is quite experimental, and I think again this is how you gain that intuition behind how things work. So continuing further, I'm sorry for always going on these tangents. I also want to give out some knowledge that might be a bit pragmatic. You can create a variable like so, and you can define its initial value as well. How do you find out what all parameters can you pass to a function? By doing this. So there you can pass the shape, the data type. Let's see if there's anything else you can do. No, not anything that I might be interested in. So that's how you check what parameters can you pass. So we initialize it from a normal distribution of the shape like so. And if you want to assign new values, you do them like so. So if you want to change the value inside of v, there's an assign function that you can call. You can also do it like so, where you index into a certain element. So the element at 0, comma 0 and assign it this particular value. You could also assign an add. Let's see what this does. Let's search assign add inside of the documentation. TensorFlow is by Google, so their search should be good. I'm hoping it is. It just adds the number, but I was trying to point that out in the documentation. So this was not helpful because I didn't see that. Maybe it's quite obvious to everyone, but I didn't see that. So I downvoted that. Uh, we are adding 1 to this entire tensor. How do we do that? So we call the function assign add, and then we pass the tensor that we want to add to it. It is a tensor having all ones because we're calling tf dot ones. So we would just add 1 to all of these. Yes, logic checks out. It does add 1. Why are we looking at all of these functions that are so basic? Turns out deep learning is a bunch of matrix operations, and it's important to learn these because you will be just doing these at scale eventually. So that's why we're spending a bunch of time here. To anyone who's experienced, I see incredibly smart people in the chat. I'm sorry, this might feel like a waste of your time. I also want to be thoughtful towards people who are just starting their journey. That's why I'm going slow initially. We'll speed up towards the next lecture, I believe. Again, this will be more focused towards the basics. Let's look at a few math operations. It's a bunch of matrix operations, right? So how do we perform them inside of TensorFlow? We define ABC as tensors, sorry, A as tensor, having all ones. And now if we want to square it, we call tf dot square. If we want to perform a square root, we call tf dot sqrt. If we want to add them, we can do it like so. And if you want to multiply, we can do it like so. Does anyone want to take a stab at how are these two different? Are these two the same? So if we do a mat mul, or if we do use the shorthand operator, this basically, for anyone that is new, is usually used to represent this. But if we are using a shorthand operator, does anyone want to take a stab how this stands out? What does this do? There's a little delay between when I say the words and when it's live stream, so I'm taking a pause to just check. Katie is right. It's element wise multiplication. Martin as well. Thanks for those answers. We went into depth about gradient tape. As a reminder, it's used for tracking gradients. But isn't this counterintuitive? Like if you've been in the PyTorch world, why do you like need to understand a separate term that tracks gradients? You don't need to. For important variables, the book claims that it's auto tracked, so we don't have to worry about the variables that we want to differentiate. But it's still important to learn how it functions. So inside of the book, I believe they use an example where we calculate a first order and a second order gradient. I wasn't good at calculus, so I'll try to explain this. A first order gradient is when you differentiate something for the first time. So speed is a first order gradient, and acceleration is a second order gradient because we differentiate speed to get acceleration, which is what the example in the book does as well. I'll skip over here because that's what's happening here. So now we are well equipped to create an end-to-end example. Inside of the book, Franco mentions this is a filter question for interviews. So phone screen question, which means this is quite a vanilla example. It's still an end-to-end example because we are training a model that is a linear classifier in pure TensorFlow. So we create, I think I'm just trying to look here. We create 1,000 samples and we create negative and positive samples. So we are trying to create a cluster of two samples that we want to separate via a 2D plane. I'll use this image to skip my hand waving. And what we want to do is we want to, as a potential machine learning candidate who's interviewing for an awesome job, to pass the phone screen, we need to classify these and use a linear classifier to prove that which point belongs to which class. So we've created these clusters of points and we've done a scatter plot. I am always tempted in my learning journey to, look up what is a scatter plot. Don't do this. Don't go down the Wikipedia rabbit hole. Please don't do that. You will end up learning a lot about the theory. But what you want to learn about it is what's happening inside of that matplotlib function. Please, I fall into this trap every single time of not spending more time fiddling around with the arguments, changing the value, seeing how that works. So I'll keep mentioning this until it gets annoying, and I'll continue even after that to anyone who's new, because it's a mistake we all make. So what we do next is, now we have 1,000 examples. Uh, I won't count this, but I trust NumPy to have created 1,000 of these. So we have 1,000 classes that are positive and that are negative, and we want to create a classifier. So to create our data set, we stack this by calling numpy.vstack. You can look at the signature to see what it does. It just stacks these arrays on top of each other. And then we also would want to stack the targets, right? So let's say it's a linear classifier. So we can just assign a number 0 to one cluster and 1 to another one. Now we can take a plot that I was using and take a look at the plot to see if everything is right. It's always a good idea to print out things to plot them to see if they are working the correct way. So as a potential candidate, now we're ready to create the linear classifier variables. We set the input dimension as 2, output dimension as 1. We initialize the weights and biases like so by utilizing the input and output dimensions that we've created. See the subtle difference of not passing these numbers in here. These are things that you should be careful about. So if things break, or if you want to change these, you should change them here and not paste them here, because maybe not for this example for sure, but when you're working with a multi-headed transformer model, things get out of hands really quickly and it's like impossible to debug, especially at 3 a.m. and you've been coding all night. So it's better to code things above or put them in different variables. So now we'll define the forward pass. And our model is quite simple. It's a matrix multiplication. Things won't change from here. Uh, we'll just do matrix multiplication a lot of times, even for neural networks. This is a binary classification problem, so we can define a mean squared loss. And we'll just, we could also use a different loss function here. That was an incorrect argument. We'll set a square loss for our linear classifier for this particular case. I don't want to generalize that argument. Sorry for the confusion. So having defined a loss function, having defined a forward function and our variables, we are ready to define the training step. And this time we'll have to manually tell TensorFlow, hey, TensorFlow, these variables that you might discard, these are quite important, because this task is pretty important for me to get into the next interview. So please track them. And we track the gradient of the predictions and loss. And then we can differentiate it with respect to the weights and biases to get the gradient. And then we can update the weight by multiplying the gradient with the learning rate. So the learning rate will decide how fast things will learn. And again, we're not setting this as 0.1. We're setting the learning rate here, and the learning rate is defined above. It's always a good practice if you're new to machine learning to define variables like so. You can imagine this being used 50 times inside of a deep neural network, and you don't want to change that number everywhere. You could find and replace, but that's not ideal. Now we're ready to start set up the batch training loop. We say 40 is a good number. My intuition tells me that. So we'll train it for 40 times and we'll print the loss function every time. And we'll plot the classifier we've built, and looks like it's learned pretty well. It can divide these two categories quite well. That's a linear classifier using just TensorFlow. Any questions so far? I'll take a quick pause to check. Amazing. I'll continue further. I'm always nervous as well because there's like a 30-second delay between me asking the question and then the chat coming in. This is quite vanilla stuff, so I apologize to the advanced people, and to the beginners, I'm taking a pause for you because I want to welcome your questions. Now let's understand the core Keras API, which is the most exciting thing. I assume everyone is here to learn about Keras. So, inside of the chapter, they explain why layers are the building blocks of deep learning, and we learn about the base layer class in Keras. If you want to learn more about it, let's head over to the docs and see what we can learn from there. Layers are the, it just says the same thing. A layer consists of a tensor in tensor out computation. So it takes a tensor and gives out a tensor, does some computation on it. It has a call method and some state that is stored. So it remembers the numbers. A layer instance is callable just like a function. So we could define a layer, a tens layer, having 32 units like so, and tell it to have an activation of ReLU. We can then define the inputs and outputs, and outputs are defined by passing the inputs to the layer. So that's a vanilla introduction to it. We just mentioned a layer maintains a state, and the state would store the kernel and BIOS inside of it. You could also create custom layers, and there is more in the docs that you can check out to learn about this. So that's a introduction to layers. Now we know they're like layers inside of a neural network. So let's see the example from the book chapter. If you were here in the previous session, we built a naive dense model where we took TensorFlow and from scratch, quite painfully, with a lot of lines of code, implemented a naive dense model. Here we'll take the liberty because now we're a qualified machine learning engineer who just made it through the phone screen interview of classifying two clusters with a linear classifier. We'll use keras.layers and we'll define the simple dense model like so. So inside of the constructor, we take in how many units do we want, which activation function do we want. I would say you could also, instead of none, set this to, I don't know, ReLU or something. And then we build the model where we set the input dimension, the weights, and biases. Every model is supposed to have a call function. So we'll define the call like so. Y is used to define most of the times the output in mathematical notation. So the output is the matrix multiplication of the inputs with the weights, and we add a bias to it. If there is no activation, if there is an activation function, it's double negative. So not none. We assign the activation function and return the same. And now we can call this function. Again, this is a simple dense model because we can't train it. It just takes a pass and returns some values. Not the most useful, but quite a good tutorial to start on. One of the useful things is when you're defining layers, you don't need to rely on what would be the input size. That would again restrict your code in weird ways or have you write a lot of checks. You don't want to do that. Machine learning engineers don't like doing that. Software engineers don't want to do that. But here's how it's useful. So if you want to just define a few layers inside of a sequential model, what's a sequential model? Let's first understand that. There's a sequential class. Groups a linear stack of layers into a model. Provides training and inference features on this model. It looks like it takes care of a lot of things. Uh, to me, it sounds like it'll just take whatever we tell it here and just stack them as a few layers. So all of the dense layers that we pass through the sequential function by either using add or inside of our definition here, passing them like so inside of a list, they'll get stacked together. And it'll take care of the training inference features on this model. What I want you all to pay attention towards is earlier we had to define the input and output shapes, we had to take care of those things. Here we don't. And that's why it's really powerful and useful. You could define a custom sequential model that you derive the knowledge for, like so, where you pass simple dense models that we had just defined. So we're defining a custom model based on a custom class we had defined earlier, and that should also work. So how do we get a model out of it? Now we've learned to create this simple dense model. How do we get the model that we can train and deploy in the real world? Uh, this is a bad example. You never would deploy such a model. Maybe you would, maybe you might. Uh, but again, this is for our understanding. So with that warning out of the way, we have defined a sequential function by calling just one dense layer. So we've just passed it one dense layer with one unit inside of it. Now we'll compile the model. So let's see what compile does. The reason why I'm defaulting so much to Keras documentation is because I think it's terrific, quite. I'm trying to think of terrifically written. Is that a word? I don't think it is, but it's written really well, and I think it's a good starting point. So that's why I'm defaulting here again and again. It configures the model for training. That's the only thing we need to know. Now we're good to go. Let's see what arguments does it take. Optimizer, name of the optimizer or its instance, loss function, matrix that we want to evaluate during training and testing, loss weights. What are these? The loss value will be minimized by the model and then a weighted sum of all individual losses. So remember how I told you earlier, instead of looking up different theoretical concepts inside of the documentation, you'll find more practical knowledge. Now, if you're curious more about this, call it inside of this simple function and print it out every time. See what it's doing. That'll take that'll take you further than just understanding the theory. So there are a few more arguments that you can pass. Then there is another function. I'm continuing because this is also there in the example. Fit method is similar to the scikit-learn fit method. So now we have configured the model for training. We would like to train it. So this trains the model for a fixed number of epochs on the dataset. It can again take all of these arguments that I invite you to check out after today's live stream or in your free time. And one more method that we need to learn about is the evaluate method. So this returns the loss value and matrix for the model in test mode. That's the keyword. So far, the fit would just do it on the training data set. This would be the test mode where we are just, as the name gives away, evaluating the model on a test data set. And then there's a predict method as well, which assumably after you have a trained model, you can generate predictions from it and you would call it to just get those values. So these are the 4 or 5 functions that I wanted to point out. Now we compile a model, tell it, please use the optimizer, sorry, RMS prop. Please use the loss value mean squared error. See how simple our life is now. Earlier we had to define all of this quite painfully. But now since we've passed the phone screen test, we can do all of these things with Keras. Then we can simply compile the model by passing these. You could also uh, grab these like so if you want. So inside of the Keras modules, you can call these different things. Um, I'm trying to recall if anything important is here. Uh, Franco mentions inside of this chapter how you can pick a loss function for different things. Here's another way of doing the same. If you want to learn what loss function should you apply to a particular problem, go to Kaggle, find a similar data set. So let's say you want to protect reefs as well, and you have a similar data set to this one. Look at the data set and see how it's being evaluated. And there you go, you learn about something new. And you can use the score and see if you're evaluating well. So if you want to figure out what matrix should you use, for what loss functions should you use, this is a good way of evaluating the same. Can you provide, I'm sorry, I'm looking at the chat. Can you provide the link to the Keras recap repo? Sure, let me quickly grab that. Um, I had just shared you Raj's work, so I'm trying to find that real quickly. This would be the recap. It is there in the YouTube chat, and let me also put it in the platform chat. Okay, I've shared the chat, and I hope the person is not upset. I want to make sure they know the link. Um, Coming back to this example, that's how you can pick a loss function. You don't want to annoy a loss function. Now let's understand the fit method, and it also tracks the history. So if you just print out the history from a fit function, it can tell you the different things it's been through in life, and inside of its life it's been through all of these losses, loss function, loss values, sorry, accuracy values, and we can track that like so. Now inside of the chapter there's one important lesson that I'll quickly try to unpack here. You also want to make sure this model generalizes well outside of what you're training it on. And the way of doing that is setting aside a validation set and also setting aside a training data set. You never use the training data set to tune your model, and you also just use the validation model to look at how your model is performing. You don't train on it. If you want to learn about this further, I would encourage you to check out this blog post by Rachel Thomas. How and why to create a good validation set. Rachel is one of the best, I would say, bloggers in our world, and she has also co-founded FastAI. So I would really encourage everyone to take a lot of inspiration from her work and try to replicate something similar when you are writing something. So read that blog post to understand why validation data sets are important. Here, we're doing a simple thing of setting aside 30% of our training data set that we'll never use for training and just use as a way of understanding if our model is not just memorizing everything inside of the examples. So we set aside the validation sample and we can pass validation data like so. Then you can run inference inside of this chapter. There's also comparison between batch training and mini batch training. So this would be mini batch training because we're not training on the entire data set. That is a quick summary of chapter 3, and I'll take a 30-second break to answer any questions if there are any. I see an awesome question by Himanshu. There's a discussion, and he points to the specific section. So, to anyone who has the book, section 3.1.3, thank you, Himanshu, talks about the best practices for loss function. But what are the best practices for optimizer? That's an amazing question. And what are the best practices of comparing optimizers? Boris Dema, who also works at Weights and Biases, he builds incredible projects like Doll E Mini and Hugging Tweets. I would encourage you to really check out his work. Let me put that in the chat there. He had shared this comparison of different optimizers. So let me point you to this tweet. If you go to his profile, that's easier to share in the chat, right? I assume everyone is seeing this link right now. I don't want to point you towards the tweet. Just go there, scroll down, and you can find this comparison and also incredible blog post to go along with it. He had actually asked this question as well: what optimizer do people use these days? So it's quite seasonal. In winters we use a different optimizer. I'm just kidding. It varies depending on the problem. And as you can see, it got quite a bit of engagement. Please see that thread again. Check out Boris's profile, scroll down, find those incredible resources, check out his work, and see that discussion to understand what optimizers are used today. Thanks for the great question. I believe it was Himanshu. Thanks for the question, Himanshu. Sorry about that. Amazing. So we've just finished chapter 3. We are, I think, 20% into the book. That is awesome. We've completed 20% of the book in just 2 sessions. I assume everyone would read faster than this. So sorry for being a bit slow if you can read faster. Now we are excited to get started with neural networks and we learn what classification and regression is. Remember when I said I would encourage you to check out the datasets from the Keras datasets module? We're doing it anyway. So I gave you homework that would have spoiled things. But now we're looking at IMDb and let's see if I can print something about it like so. I wouldn't assume that might work. No, it wouldn't. So what I'm trying to do here is I want to find out things about IMDb from the documentation. Head over to the datasets. And these are the datasets inside of the module. So this makes our life really easy by loading the IMDb dataset. What is the IMDb dataset? That's not helpful. Sorry, Stanford. This is a dataset of 25,000 movie reviews from IMDb, labeled by sentiment, positive or negative. Reviews have been pre processed, and each review is encoded as a list of word indices. So remember, our neural networks they can't take in words, they need numbers because remember, we are doing matrix multiplication. Looks like this dataset is about that, and it makes our life quite easy by doing a lot of those things. So we import that and we can create train data and train labels like so by loading it. And we just look at the top 10,000 words. How do I know this? What this function is doing? Because I looked at the signature by putting a question mark and looking at what's going in there. So let's see what's inside of our train data. It's a lot of numbers, and these numbers would be mapping to a particular word out of the top 10,000 frequent words inside of our data set. So that's what this model is doing. And then we can take a look at the label as well. So the label for this particular example is, I think, positive. We can also decode these back and take a look at how long does it take. Does anyone want to answer why are we subtracting 3 here? So when we reverse the word indices, we are creating a dictionary where we are passing the items and also the decoded version of the review. So when we are trying to get the indices, does anyone want to answer why we subtract 3 from here? It's like I'm living in the future because I'm 30 seconds ahead of the live stream and I have to wait for the chat to come in. So whenever we take words and encode them as numbers, there are three things that are always common. So unk, which is unknown pad, and another one which I'm forgetting right now. So a suggestion, please print these out and see what those are. But there are three tokens which are unknown, pad, and I'm forgetting the third one that are always encoded. So that's why we are subtracting 3 here. Inside of this chapter, what we are really learning is how to create a model that can work with classification and regression problems. So this is a classification problem because what we want to achieve here is we looked at the IMDb dataset, and using those movie reviews, we want to classify by just looking at the words and telling if it's a positive or a negative review for a given movie. So we encode those integer sequences. Even though we have numbers, we can't simply input them to our neural network. We need to find a way of creating a tensor, and we do that by multi-hot encoding them. So we define a function that we call vectorize sequences. It gives it away, but we want to vectorize, create vectors out of the input sequences. And the result is a zeros having numpy array having all zeros with the dimension being the length of sequence and 10,000 words. So we are trying to encode all of the 10,000 most frequent words into this. And we do that by simply setting those particular values 1 wherever that word occurs. Now we can print. I'm assuming everyone knows what multi-hot encoding is. If not, please ask a question and I'll explain it further. Now we can take a look at the train array, I believe. Yes, it's an array. And we can define the test one like so by calling the test labels. And we're ready to build our first classification model. It's a simple model having stacks of layers because we just learned what sequential is, where we call all of these dense layers and define the activation functions like so. Inside of the chapter where they explained how you should call activation functions, they gave you the intuition of which ones should you use. So assuming you are aware of that, we'll call sigmoid here. And now we're ready to compile the model, set aside a validation data set, fit it, and there we go. We have an accurate model that works really well on movie reviews. The thing that the chapter teaches you is also overfitting and underfitting. So the dots represent the training loss. And so far, we've just been concerned with the training loss, right? But we just learned about validation dataset. And I gave you the homework of reading this incredible blog post by Rachel Thomas, which will tell you the importance of this. But I'll give you the summary. We want the loss to be minimal, not just on the training dataset, but also on the validation dataset. Our validation dataset is a proxy to the real world and will tell our team how good is the model at performing in the real world. So models are really prone to just learning the details of your data set, and we don't want that happening. How do we avoid that? We use a bunch of tricks that we'll get to later, but there are ways of avoiding this, and that's one thing you should be always careful about. You don't want your model overfitting. We've looked at this graph. Here's how you understand model is overfitting. The validation loss is much higher than your training loss. So that's a sign of overfitting. Another sign, it first improves. So the loss improves, which means that the loss value goes down, but then it gets worse. So that's a sign of overfitting. I think I'll skip these further because I don't think there's something I want to point out from here. The next one is a multi-class classification. So we use the routers dataset. I leave you to check out what that is by looking inside of the documentation. All of the steps here would be quite similar to some extent. We get the word indexes. We also see how long does it take to reverse it. Remember those three words that we always subtract. We do that to decode the dataset back. We set a train and dataset. We one hot encode the labels. And this time we call something new. We call a util that is two categorical. So we tell Keras, please Keras, these are not just numbers, these are categories because remember we are looking at multi categories now. And this time we build a model with a soft max layer at the end. And now we can do the same things, validate our approach, and the model would be trained. If you want to test how well does this model perform, you can call the predict function, which we had looked at earlier. And you can call it on your test set from where you can test the test accuracy. It is a sin. You will go to the hell of machine learning to train your model on the test data set. You never fine tune it on the test set. Always avoid that. Write that down. Never make that mistake. That is a huge red flag and never do that. So we are just evaluating by predicting here. Never train on your test set. Scrolling further, I'm just making sure if there's anything else that I want to point out. There's another example, there's a regression problem. It's well documented, so that's why I'm just pointing out the little details inside of the book. There's well documentation around it. So now we're tasked with predicting housing prices. And this again comes from the data sets. You can look inside of the documentation. So there are about 400 training examples, 100 test examples. Looks like a good number. This time we want to prepare the data by normalizing it. So we do that by dividing with the standard deviation and subtracting the mean. And we build another sequential model. This time, there's no activation function on the last layer. It just gives you a number because we want to predict the price of the house. So hopefully our model will do a good job of just predicting that. Inside of this book, inside of this chapter, we learn about K-fold validation. So if you have a smaller number of examples and you still want to set aside a validation data set, see the problem here is 30% of something small is very small. So you don't want to do that, right? Here we'll use something known as K-fold validation, where we'll take a data set. I'm trying to see if there's some cloth around here, but basically you fold your data set. That's how I understand it. So let me stop my screen share. Sorry, I just disconnected my headphone. Give me 1 second. I can just get rid of them. We take a data set. Hopefully, it's not a jacket. Uh, there's a question by Katie. What is a small data set? I'll just come to that. And K-fold validation folds your data set into different parts. And then you train on these different folds by using a way of selecting them. That is K-fold validation. So the number of folds is how many times you fold your data set. The creases define the boundaries, and we train our model on these different folds, all of which have a validation data set inside of them. And the final validation accuracy or loss is an average of all of these. Great question by Katie. What is a small data set? I'm not an expert to answer this question. I've uh, not put many models in production. I have spent more time sharing these resources. Uh, but with that caution out of the way, you always want to set aside 30% as a rough metric of your training data set for validation. If your data set has 1 million examples, 30% of that is a huge number, relatively speaking. So there you would set aside a smaller percentage of the validation data set. How do you understand this? It comes through experimentation. 100 house examples would be a small number, I would say, to predict. But one thing that Jeremy Howard has taught me in Fast AI, he mentioned this in one of the lectures. You would always overestimate how much data do you need. So there have been blog posts by many of my Fast AI classmates that showcase you that even with 30 examples, you can do really well. So always start with whatever data you have and go from there. Probably will always remember the K-fold example with my jacket. My jacket is quite happy to make a contribution in your learning. Let me share my screen again. Select the right window, which requires a lot of complicated head scratching, and hopefully I do the correct screen. I do select the correct screen. Awesome. I'll continue further. It's a bit tricky talking to the audience and also doing an operation. I'm bad at multitasking, so sorry for the stammer. So this is what K-fold validation is. I wanted to give that example out there, and this is what we are doing in code here. I'll glance over the details, but we set aside 4 divisions inside of the data set, and then we average across all of these for our matrix. So we print out all of these scores, and then we call np.mean. What is that? Put a question mark and check what that is. Uh, it'll tell you the details and tell you all of the magic. And looks like you can pass a list and get a mean out of it. So maybe you don't need to look at it. It takes a mean of all of these, and that's the number that we care about. Um, I just wanted to point this detail out again, being conscious of everyone's time. That concludes the chapter 4 summary. I still have the ambition to go through chapter 5. So let me see if I can get to that. But before that, any further questions from this? Katie, please let me know if that wasn't a useful answer because I know it was quite vague to what is a small data set. Sorry about that. Amazing. I don't see any questions, so I'll continue further. Let me close this tab. Close all of the documentations. I also have a group exercise that I want to get towards in the next bit. I'm just quickly scrolling to the bits that are important. Amazing. So I mentioned earlier that you want your model to generalize to the real world. This chapter talks about a few things. So we go back to the MNIST model, and this time we randomly shuffle the labels. The chapter goes into depth about underfitting and overfitting, and why is generalization important. The concept of concept drift. So the concept of concept drift. Uh, I wanted to confuse you all. There's a concept known as concept drift. Again, did that mistake, which tells you that assuming you want your, let's say you want to create an app that classifies hot dogs or not hot dogs. And let's say TikTok creates a trend where people, for some reason, start putting green sauce inside of hot dogs. And now all of your images coming to the model have green sauce. Your model probably wouldn't predict that as a hot dog because it's never seen a hot dog that I've never eaten hot dogs. I'm a vegetarian, but I would assume it's a sin to add green sauce according to your model, because now we are drifting from the original model or original data set. The original data set had mustard and ketchup in it. Now the model doesn't know what to do or what to make of the green sauce. So that's a concept drift, and that's why we always want to retrain our model on the correct data set. And that's how you can also think of concept drift as an example. We want to make sure our model generalizes well. Then we learn about overfitting and underfitting. I'm scrolling quickly because there are 10 minutes to go and I want to unpack a few things before ending. So we set a very optimistic learning rate for the first one, and our model doesn't train so well with that. And then we try to set a more appropriate learning rate. You might be tempted to ask what's an appropriate learning rate. It comes through experimentation. So in this experiment, in one of these experiments, we observed the model is not fitting really well. These numbers aren't going down as they should, because see, the validation loss jumped here and it's going up and down again. So maybe that's not a good learning rate. You might be tempted to change that. If that doesn't help, you might be tempted to add more layers here. You might be tempted to change or look at your validation data split. Those are a few things that you can do. So we are looking at the problem of what to do if your model isn't training well. There are a few other tricks known as regularizations. So you can regularize your model. Sorry, I recalled this by memory, but later in the collab, they show you how to increase the model capacity and they show you how it improves the accuracy. So you can improve generalization by doing the following things. You can curate more data. You can do feature engineering. I think data curation is quite straightforward. You can get more data and train your model on it. Feature engineering involves smart domain knowledge. So let's say Somehow this is really hard to do, but you add a feature that checks if this is green sauce and if this is hot dog. So you find a way of telling your model green sauce yes, hot dog yes. You've engineered that feature, and now your model can tell, hey, it's still a hot dog. Some TikToker mailed everyone. Go crazy and add green sauce to it. So that is feature engineering of encoding this domain knowledge of TikTok trends into a model that then the model can leverage, or encoding your domain knowledge of whatever field you come from for the model to be able to leverage. Sorry, I was just looking at the chart. You can use early stopping. The name gives it away, but let's. If you're ever confused about a concept, right? My default intuition was to Google it. Don't do that. Go to the API docs and see if you can find it there. So what were we looking at? Early stopping. Stop training when a monitored metric has stopped improving. Our uh, bosses don't care about a model once it stops improving, because that makes their cloud expenses go up. So this is the way of reducing our cloud expenses or stopping our model from training further. Assuming your um, I'm trying to think of a good example, but assuming your accuracy stops improving, that means your model isn't training further, and that is a good sign to stop training from there. And then you can also reduce the network size. There is another technique known as dropout. Again, I'm speeding up a bit because I had this exercise that I'm excited about, so I want to get to that. But you can add dropout. What is dropout? Let's take a quick look. It's a layer that applies dropout to the input. Not very helpful. Uh, it randomly sets inputs. First line wasn't helpful. Second line is randomly sets inputs to zero with a frequency of rate. An easier way of recalling this that someone told me, it's like getting your model drunk. So it will randomly forget different things with a rate equivalent of how drunk it is. Uh, Basically, you take different weights and with a random probability delete them from the model. That's what dropout does. I think I'll come back to L1 and L2 regularizers and we can continue the lecture from here. But I want to do this exercise now of going through the important bits in chapter 6 by asking everyone this question. So we can either do this as an example where we go through this exercise. So let's say you are getting paid money now and you're offered money to build a ML system, and your task is to help a business improve sales. So let's say we can do in role play, or we can look at what questions should we need to ask. But we've been hired by different stakeholders that want us to increase their food sales using this black box of machine learning. So I can play as the stakeholder as well. I can play both sides. But what would be the first steps here? How would you go about doing this? We can also look at another problem, but we can maybe just start here or go with this. So you've just been hired to improve food sales by using machine learning or data science. What would you do as your first step? What questions would you ask? How would you approach this problem? How do we formulate this problem? I'll give the chat a minute to catch up. I'm looking for comments that anyone might have. I don't see a question a comment come in, which is embarrassing. But I'll continue further. So I'll copy paste this into the talk, and I was hoping to go about the steps of um, formulating what we learned through chapter six. So chapter six tells you about the things that aren't the most shiny parts of machine learning, which is defining the task, defining the problem, collecting data sets, all of that stuff. Katie has an amazing comment. Thanks, Katie. She suggests she would ask what the constraints are. So, putting my stakeholder hat on, um, the team budget salaries would be the constraints here, but that's always one of the major constraints. Sorry about that side tangent. To increase sales, you could always reduce the price. That's a valid point. But what I wanted to do by giving this vague idea was boil it down to the right part. So let's say think of any major app, think of Uber Eats, think of Swiggy if you're from India. Your job is to create a better recommender engine. That was what I was trying to get at. The stakeholders want to create a recommender engine, but they have formulated the problem of improving food sales. So, Katie, the constraints here would be, let's say, we don't want to lose our existing user base. We are okay to do an app redesign, and we want it to be a similar experience. These would be the constraints. Akshaya suggests maybe ask about the food variety options available. Uh, sure, we can ask that question as well. So we could. I'm always nervous when typing, but it makes the fact that I'm doing this live makes it a bit harder. Sorry about that. Look at the data. See what more comments are there. Oru mentions, thank you, Oru. That's an amazing comment. Clarify what sales mean. So the sales, this would have helped us unpack this comment that it's an actually recommender engine problem. But sales here means we have an amazing app. We have an awesome food delivery app through which people order food. The amount of food bought or delivered is equal to sales. I see a comment by Yuvraj. He would check different features into sale of items like food category, time of the day, time of the week, create a data set with these features. That's awesome. That's an awesome comment. Thank you for that. I was first trying to formulate the problem. So far, let's get that step done. So far we've managed to narrow this down to a recommender system problem. We understand that the stakeholders maybe don't. They just want machine learning go burr and get more money out of it. So what we want to do is inside of the food delivery app, we want to customize maybe as we understand we want to give people the better options. So if you like ordering lunch, we could figure out what they might want. We could use machine learning to see what people order during lunch, maybe in an area, make that the first option. So far we've managed to narrow this down to recommender engine problem. So the first step here is to take the broad statement, convert it into a machine learning problem, right? Now it's a recommender system problem. Next step, for which Yuvraj had an awesome comment, and so does Prabir. Thank you for that. Now we need to see what data do we have. So we tell our stakeholders, hey, can we please get access to your data? And they shoo us away telling that, no, you're an expert, you need to bring your own data. So for that, we need to, maybe we could try reconvincing them, but let's assume that's not an option right now. So Prabir also asked, do you have past sales data? Do we know details of customer? Do we have data across various items you sell? Do we have data across time and geographics? These are all awesome questions to ask. So let's say our data has sales, time, area, food, restaurant, and then you can have like side of the restaurant, you can have the ratings, how many deliveries are they making, so on and so forth. Um, there are any other things? They tell us this is all we have inside of the data. And assuming they don't give us access to this data, you could try finding a similar data set on the internet, but maybe you are able to convince them. So the next step would be performing rigorous EDA, exploratory data analysis on this. You look at the data, you now go about the steps that Yuvraj had mentioned. So you'd see if a certain food category is doing well. You can see if I'm ordering chai. I'm an outlier. I would order chai the entire day. So maybe you'll find me as an outlier, this person who keeps ordering chai for any random time. But you would want to understand trends inside of the data set. You would want to understand what does this data set have, what are the areas covered with it, are there any missing values, how detailed is the timestamps, do we have timestamps for all orders, are people returning them, does the, assuming we have details of a delivery person, is that affecting that? It could give us interesting insights. But now we have to go back to suggesting options. Since we've already looked at a recommender system, sorry, we have already looked at the data set. We'll start with the baseline. And the baseline can be the dumbest possible model that you can build off. Spoiler alert, it can even not be a machine learning model. So what do? I put most order stuff in a neighbor net. Sorry, I said neighbor net. Most ordered stuff in a neighborhood becomes a better prediction. We are yet to define how do we evaluate this model, right? So this is a baseline, a stupid model. It's just copy pasta, pun intended, uh, that we do. So we start with a simple baseline, and then we also figure out what metrics do we care about, what loss values do we care about. And now we have this simple, pardon my grammar mistake, we have the simple baseline that we can only improve on, right? So now you can use all of these skills we just learned. You can feature engineer, you can create a model, you can create a deep neural network, a sequential model, all of these things. But it should be better than this dumb model which just tells you what your neighbors are ordering, right? And we probably don't want that in our app. So we'll start with that baseline. And now we'll start with modeling. And then we can go about improving this model. From there, you might get accuracies. This is the smallest part of the training pipeline. I was looking at my notes in the book. You can improve your model, you can regularize it, you can change the loss values. Sorry, you can change the architecture details, do all of those things. So you'll spend all of this time modeling, and now you're ready to deploy this app. But before deploying it, you need to communicate all of this. So to do that, It's a good example inside of the book, but you need to be transparent with the stakeholders. You just tell them that, hey, this will only work in a certain area because that is quite rich, and we would like to start from there because that area is rich in orders, and we believe that we can get good info from there. So communicating to the stakeholders that, hey, this won't just connect to your brain with a neural link and tell you what you want to order. No, it won't do that. It'll just suggest you what's trending in your area. And then we can deploy the model and start evaluating. So we can see if users are using the app more, if the orders are going up, if the sales is increasing, if our model is working well. We could also not give this to everyone. We could also start with a subset and just do an A/B test. So where we give the model to a certain set of users, see how the sales are performing in that group versus the other group that does not have this recommender system. And then if we get a clear sign that, hey, people with the recommender in their app are ordering more food, we roll it out to everyone. And then we make a lot of money and retire. But with this exercise, I wanted to invite you all to learn these different steps that exist inside of, uh, as the chapter says, the universal workflow of machine learning. So the first thing we did was I apologize. I did a bad way of framing this. I wanted to, have you all ask a few questions where we figure out that this is basically referring to a food delivery app that wants a recommender engine. So assuming you had asked those questions, we wanted to frame this problem as a technical problem. Then we want to understand the data by performing EDA. Start with the baseline that we always can beat. And if you're not beating that, we're doing something poorly. Build a model, deploy the app, communicate all of the constraints throughout, and then evaluate. So, broadly speaking, these are the outlines of taking a business problem and converting them into a ML problem. We're 2 minutes over time, so I'll quickly take any questions, but this is what I wanted to cover. We've managed to accomplish my ambitious goal of getting through chapter 3 to 6, so I'm quite happy about that. But I'll take any questions very quickly to wrap up fast. Himanshu had suggested you could scrape restaurant reviews. That's a great suggestion. You could totally add that as a feature. After building the baseline, see if that helps. Amazing. Since we're over time, I'll take the questions in the next live stream. I'm always worried about when there's no chat coming in. Maybe I'm doing a good job or maybe I'm doing a terrible job. It's either of those. But thanks again, everyone, for joining. We'll go through chapter 7 to 9 in the next live stream. Again, please, guys, I want to remind this to everyone. The new variant is supposed to be less mild, but it's good that you don't catch it. Please wear a N95. Please try to stay indoors and please take all the precautions. That's one message I'll again try to get across. I hope you enjoyed this session. I look forward to seeing you next week. We'll understand ConvNets, neural networks, and also hopefully build a segmentation model in the next one. Thank you again. Please consider contributing to 27 days of Keras. Here are a few suggested homeworks very quickly. You could take this exercise and build it. Try scraping a data set that you can find on the internet, actually take and build that model, deploy it. Uh, I wanted to mention you this paper to you all, but where I was getting to that would be translate a model from PyTorch to Keras. I think you're at the point where you can start going over the PyTorch examples and write them as Keras examples. This won't get you far. This won't get too far on your resume, but this is a good way of learning Keras. And then, as a suggestion, create a deep learning model on TPS competition just for the kicks of it. Please consider contributing to 27 days of Keras. And with that, I'll wrap up. Sorry for going over time. Thanks everyone for joining, and I'll see you all next week.